In the last video, we have defined what it means for a point A inside a variety X to be smooth. Namely, we have seen this is equivalent to saying that the dimension of the tangent space TA of X is equal to the local dimension of X at A. But this is all good and well, but then how do we determine the locus of smooth points and its complement, the locus of singular points in practice? We want to have something which we can really calculate with. And the right thing to do is the so-called Jacobi criterion, which gives a very explicit thing that we can compute to check whether a point is smooth. And we do this here in affine coordinates. So let's say X inside AN is an affine variety. A is a point in X. And let's say the ideal has generators F1 up to FR. Then X is smooth at the point A if and only if a certain matrix called the Jacobi matrix has rank at least some number. So the Jacobi matrix J is obtained by taking these partial derivatives dFi up to modulo dxj at the point A. So here the Fi, these correspond to the rows of the matrix. They go from 1 to R. They correspond to the generators of the ideal. The xj, these go from 1 to n. These are the coordinates on the affine space AN. And so overall, we get an R cross N matrix over K. And here note, if the Fi, these are all polynomials in N variables. And then we can calculate their partial derivatives like this. These are again polynomials we can evaluate at the point. This gives us elements in K. So we just get one explicit R cross N matrix with entries in the field. And then the Jacobi criterion says X is smooth at A if and only if the rank of this matrix is at least N minus this codimension. And if we have this inequality here, then in fact automatically the inequality is an equality. So somehow this is the second part here, that once you have this greater equal, then automatically you have the equal here. So it's a very nice criterion in terms of the some set of generators of this idea. So it's a finite calculation that tells us this. And the proof is relatively short, so I'm not going to write it out live. So the first thing is that we always like it if our point A is actually at the origin. And we can we can simulate this by having these shifted coordinates yj is equal to xj minus aj, and the point yj equals to 0 correspond to all of the xj being at the points aj. And then remember that to define the tangent space, we just looked at the linear terms of the defining equations at this point, and the linear term of Fi at this point, now we can kind of remember our analysis 1. We can get this linear term, or I guess analysis 2, because it's multivariate. We can get this linear term by doing a kind of formal Taylor expansion. It's just dFi over dxj at the point A, and then our new variables are these yj. And this Taylor expansion, even though we're working over an arbitrary field here, because this is kind of just a formal sum, everything just works. Somehow you can convince yourself by, for example, plugging in these kind of shifted coordinates and expanding, and then you see exactly these are the right coefficients to put here. Okay, so we do get the linear terms, and we see already these partial derivatives appearing here in the matrix J make an appearance. And in fact, you see this here is just obtained by taking this vector of the yj's and multiplying against this matrix here. And then you get a vector, and the ith entry of the vector is exactly this thing here. And so the tangent space was defined as the thing cut out by all of these linear terms. So all of them should be 0. And so somehow we have that this vector yj multiplied against the matrix J gives you the zero vector. So in other words, this is equivalent to saying that the tangent space at A is exactly the kernel of this matrix. And then, well, we have seen in the last video that A is smooth if and only if we have this inequality here of the dimension of A less or equal this local dimension. And then, well, the dimension of this kernel has the property that it is just n minus the rank of the matrix. Because, I mean, the matrix starts, I mean, it takes an input here of n entries, an R cross n matrix. And the rank is just given by this n-dimensional space modulo the kernel by the isomorphism theorem. So somehow, when you take this inequality here and just apply the function n minus dot on both sides, then n minus the dimension of TA is the rank, and n minus the codimension x of A gives you this right-hand side. And because this function n minus dot is strictly decreasing, it switches the sign of the inequality here. And so we get this first inequality. This is part A. Or that's kind of the first part of this statement. And then what we have also seen, this was the second part of the lemma last time, that once you have this inequality here, you automatically get equality here. And then once you have equality here, you do the same operation as before, and then you get the equality that you want here. So it's always nice in this case that checking one inequality actually automatically gives you then equality after the fact. Okay, so this was just some manipulation using this lemma, which told us about this kind of characterization in terms of dimension, plus the realization that the Jacobi matrix exactly has this property that its kernel is given by the tangent space. Just combine these two properties, you get this result. And as an example, to have a picture in mind, so if, for example, in A2, you have x, a curve cut out by the single equation f, then we can apply this lemma, and we have just one generator, and then it says x is smooth at this point if and only if the rank of the Jacobi matrix is at least n minus this codimension. So first of all, the Jacobi matrix has one row associated to this generator and has two columns associated to the variables x and y on the A2. So it just is given by these two partial derivatives. And then this should be greater or equal n minus the codimension. Well, the codimension of this curve is 1, n is 2, so 2 minus 1 is 1. Okay. So we see x is smooth at this point if and only if this matrix has rank at least 1. But this is equivalent to saying that, well, this vector here shouldn't be 0. In other words, j shouldn't be 0. And so here, if I draw some kind of plane curve like this, then we see here at a nice smooth point, the j will be a vector which is non-zero. And in fact, in this real picture, the vector j will always be perpendicular to the curve. So this is basically, I mean, in analysis 2, you might have seen that kind of the gradient of this equation, which cuts out some solution set, is always perpendicular to the solution set. But I mean, in general fields K, this, well, we don't really need this. And so there suffices that j is non-zero. And then somehow as we approach one of these singular points, you can check in some example that this gradient vector j will get smaller and smaller and smaller. And at this point, actually j vanishes. And then you can check like this, that this is a singular point. Okay, so this is kind of the basic example to have in mind. And then, so now we have a criterion for checking things for an affine variety X. And sometimes it's useful to also have a criterion for a projective variety. And of course, you can always do this trick of covering the projective variety with affine patches and then checking that each patch is smooth. But in fact, somehow, as it's always, or somehow as it's very often the case, there's actually a nice formulation in terms of homogeneous functions. And so if X inside Pn is a projective variety whose ideal is generated by a set of homogeneous equations here, then any point A in X is smooth if and only if the rank of this matrix here, I should say, I guess, the rank here at the point A is at least n minus this codimension here. Note one thing. So these, you know that these homogeneous polynomials don't really make sense as functions on X. And so in general, this point A is only defined up to some scaling, right? But since these are homogeneous, also the partial derivatives here are homogeneous. And then if you plug in a different scaled version of A, then you can check that what just happens with this matrix is that you draw out a lot of constants, a lot of powers of the scaling parameter depending on the degrees of the functions fi. And so calculating the rank is independent of drawing out these constants. So somehow this is a well-defined, this rank is well-defined even if the individual rows of the matrix maybe are not well-defined. Okay. So this is a kind of nice slick criterion. And if you want to tackle this exercise, you can see in the exercise 10.13 in the script gives some more hints. Okay, so we have this Jacobi criterion both for affine varieties and for projective varieties. One slightly annoying thing here is that you still need these F1 up to Fr to be generators of the ideal. And sometimes you're not in this nice position of having this ideal fully described. Sometimes you just start with a list of equations and then you want to study their common solution set. But you don't know, maybe some of the equations are actually not nice. Maybe you would have to take a root somewhere. Maybe they don't really generate the radical of the ideal spanned by them. And so the next corollary kind of gives the criterion even in this case. And this is kind of the following variant of the criterion. So let's say F1 up to Fr are some polynomials, and you just look at the solution set. So X is the vanishing locus of those, and A is a point. Then the statement says, if the rank of this kind of matrix obtained by these partial derivatives is at least n minus this codimension, then X is smooth at A. So here the only difference to the thing that we had before is that now we don't assume that F1 up to Fr generate the ideal of X. We just assume that they cut out X in some way. Still, it says if you have this inequality, then X is smooth at A. And even better, if those are equations, if you then form the matrix here, compute its rank, and it's actually equal to R, which is the number of rows, so it has maximal row rank, then you don't even need to calculate this codimension here, because then X is automatically smooth at this point A, and the codimension is given by n minus R. So that's actually a perfect case then, because then you didn't need to compute generators of the ideal, and you didn't need to compute the codimension. Everything is handed to you. So that's a very nice thing. And again, the proof is very short, because, well, these things, F1 up to Fr, they are all contained in the ideal of X, because X is defined as their vanishing set. And so maybe they're not generators, but then we can just extend them. I mean, we can just throw in more generators until we have a set of generators. So just throw in S minus R additional polynomials to get a set of generators. And then S is greater or equal R. And then the original Jacobi criterion would look at this matrix here, which has all the partial derivatives for all the generators. So for I equals 1 to S and J through the variables. But then clearly this rank is greater or equal the rank when we just throw away some of the rows of the matrix. Namely, we throw away these extra rows and just look at this rank here. And then, so this is the rank of the matrix appearing in the theorem, in the corollary. And then by assumption, we have that this is greater or equal n minus this codimension. But if you concatenate these two inequalities, then you get the statement of the original Jacobi criterion, which says that this rank is greater or equal this. And so the Jacobi criterion says, well, because you have this inequality, this left-hand side and the right-hand side here, it follows that X is smooth at A. So that was just applying the thing that we had before. It somehow, we are here in a nice case when even though we have maybe fewer Fi than necessary, we still get the correct bound on the rank, and then this thing is automatic. The second property here, let's say we have rank exactly equals to R. Then we would like to show that then R is greater or equal this n minus the codimension, because then we would be done, and we could do the first part. So we need an estimate for this codimension here. But well, we have R equations. And we know by Kroll's principal ideal theorem that whenever we impose an equation, starting from, of course, this affine space AN of dimension n, whenever we impose an equation, the dimension can at most go down by 1. So if you impose R equations, you show that all components xi of x have dimension at least n minus the number of equations, so n minus R. And so the codimension of x at the point A, this is the maximal dimension of an irreducible component containing A. And well, all of these are greater or equal n minus R, so this maximum is also greater or equal n minus R. But then we are in business, because now we have another chain of equalities here. So the rank of J by assumption is I guess equal to R, in particular greater or equal R. And then R is also greater or equal this n minus this codimension. This just rearranges this this inequality here. And so we have rank of J greater or equal n minus codimension. And so X is smooth at A by part A. And then we also saw that that in this case, actually the equality holds in all of these cases. So you actually have that rank R is equal to n minus codimension J. And having this being equal to this also forces R being equal to n minus codimension. And then you just solve for this codimension, and then you see this codimension is equal to n minus R, just as we claim here. And so this is a very nice criterion to actually compute things in practice. Okay, and then one more thing that I wanted to mention is that you might have seen this Jacobi matrix before in this lecture, like analysis 2, because there that's often the lecture in which you discuss the so-called implicit function theorem. And I just wanted to, just like Gartman, we want to point out this relation here. And so in analysis, you actually allow equations which are just any kind of C1 functions, so continuously differentiable functions from Rn to R. And then if you have such a set of functions, such that the rank of this Jacobi matrix here at the point A, where, and this point should satisfy that all of these functions are 0 there, if this rank is equal to R, the number of such equations, then, so somewhere here you have this solution set, all of these equations vanishing. Here you have this point A. If this rank is R, then the claim of the implicit function theorem is that the solution set is locally around this point the graph of a C1 function G from some open subset of r to the n minus r to r to the r. And I mean, this function G is this kind of implicitly defined function by these equations. That's why it's called implicit function theorem. And also, I mean, if you know what these words mean, it then shows that the solution set X here is at least in the neighborhood of this point, then a submanifold of r to the n of dimension n minus r. Okay. And then just one word of caution here. So I think this is a really nice application, or somehow a really nice analogon. But it's not true that, for example, if all of the fi are polynomial, that then this function g is also polynomial. So you have to be careful. There's not really an implicit function theorem in this strength here in algebraic geometry. And the best example here is this function x squared minus y to the 3, this kind of cuspidal curve that we have already seen. And then, the solution set where this f is 0 is this curve. And then you can say, well, is this locally around a point a graph of a polynomial function? Well, if the x coordinate was this function, then you would have x equals to y to the 3/2, solving for x. And if y was the function, then y would be x to the 2/3. And you see both of these are not polynomials, not algebraic functions. Even though this thing here, I mean, you can check, for example, at the point 1, 1, the Jacobi matrix gives you 2x and 3y squared. This gives you the vector 2, 3, which is non-zero. So it is smooth at this point, but kind of locally around this point is not the graph of a polynomial function. Okay, so this is everything for now about the Jacobi criterion and ways to check that what the smooth and the singular points of a variety are.